Chapter 2.2, 4 basic concepts. We have a set, a relation, function, and binary operation. So let's start with sets. A set is a well-defined collection of distinct objects. The objects in a set can be anything: numbers, letters, movies, people, animals, etc. It could be gadgets, sala set. Okay. So each object belonging to a set is called the elements or member of the set. So here we have the example. The set C of counting numbers less than 4 has numbers 1, 2, 3 as elements. So these are the elements. The notation E, this one, to indicate that a specific element belongs to a set. Otherwise, we put a slush, not an element. So in this case, I could say that 1 is an element of C. I can also say 2 is an element of C, or 3 is an element of C. But 4 is not an element of C because there's no 4 there, or 0 is not an element of C. Okay, so you have two methods of writing a set: the rooster method and the rule method. The rooster method is you have to enumerate the elements separated by comma and enclosed in a pair of braces. So let's take, for example, the set C of counting numbers less than 4. So if I'm going to write this one using rooster method, C enclosed by a braces, and then enumerate the elements. So I have 1, 2, 3. Then you have the rule method. Phrase is used to describe all the elements in the set. So in this case, I can write C, still in braces, X such that X is less than 4. But I have to make sure that your X is an element of the counting numbers or the natural numbers. So this is now our rule method. We use formula. Okay, if it's sentence, you can write X such that, then you write the sentence. Okay, but still enclosed by braces. Next, we have definition of terms. First, we have empty set or null set. So this is the set with no elements. Okay, and is denoted by these two symbols, either. So it's either you write this one or the empty braces. But okay, this one is wrong. Okay, this one is wrong. Never combine the two. Next is we have singleton set, a set with only one element. So let's say, for example, so it's just one element, singleton. You could have B, 0. Okay, you can have C, 2. Next, we have universal set, a set containing all the elements under the consideration and is denoted by U. Next, we have finite and infinite set. A set is finite if it consists of a finite number of elements. Let's say, for example, A is 1, 2, 3. So I can count the number of elements. I can have P, I'll have X, Z, and 1. Okay. Otherwise, it is infinite. Let's say, for example, C, I have X such that X is an element of natural numbers. You cannot count all natural numbers. though it's called counting numbers. Next is we have equal sets. Two sets, say A and B, are said to be equal, written as this: A equals B, if A and B have exactly the same elements. So let's say, for example, you have A as 1, 2, 3, and then you have a B which is 3, 2, and 1. Therefore, we can say that A is equal to B. Equivalent sets. It's different from equal sets. If A and B have the same number of elements, then we say that A and B are equivalent sets. So let's say, for example, A, B, C. And then your B as 1, 2, Y. Okay? They are not identical, but both have the same number. So here we have 3 elements. Here we also have 3 elements. So we can say that they are equivalent sets. Next, subset. A set A is called a subset of B, written A subset B if and only if every element of A is also an element of B. So let's take, for example, your A is 4, 5, and then you have set B 1, 2, 3, 4, and 5. Since 4 and 5 belongs to set B, then we could say that A is a subset of B. This dash here below also indicates that it could be equal. So let's say, for example, C is 1, 2, 3, 4, 5. And if you notice, B and C are equal sets. They have exactly the same elements. We could also say that C is a subset of B because of this symbol. Now, since A is not equal to B, then we could say that A is a proper subset of B, which is denoted by this symbol. Okay, remarks. The null set is a proper subset of every set. So, empty is a subset of A, B, C, or D, any set. Or you could say empty brace is a subset of B. Next, any set is a subset of itself. So if you have A is equal to AB, then we could say that AB is a subset of A. Then we have a set with n elements has a total of 2 to the n subsets. Okay, so if you have a set with 3 elements, like this one, then we'd accept that the total subsets of B would be 2 to the 3rd power, so that's 8 subsets. So later on, when we list down, at least we know how many subsets do we need. So let's take, for example, list all the subsets of A, 1, 3. So since there are only 2 elements, so we'd expect that we have 4 subsets. So let's start with A1, which is 1, 3, and then A2, 1, A sub 3, 3, and then A sub 4, which is the empty set. So 4 subsets. Next, let's have list all the subsets of A, X, Y, 4. Since there are 3 elements, so we'd expect 2 to the 3rd power, which is 8 subsets. So let's start with A1, which is itself X, Y, and 4. and A sub 2 xy. A sub 3, we have x4. See, A sub 4 y4. Then A sub 5 x, A sub 6 y, A sub 7 4. And then lastly would be the empty set. So these are the 8 subsets. Note, okay, when you write set, you have x, y is just the same when you have y, x. So the arrangement of the elements does not matter. Okay, and then when you have x, x, y, this is wrong. Okay, you write one distinct element once only, so x, y, not x, x, y. Next, we have operation on sets. Start with union. So the union of A and B, written in AUB, is the set containing all the elements which belong to either A or B or both. So you simply combine their elements without repeating the same common elements. So let's say, for example, you have here the universal set 1, 2, 3, 4, 5. You have A1, 5, B2, 3, 5, and then you have C3, 4. So if you want to have A union B, so I'll have 1, 5, 2, 3. So I don't have to write 5 because you already have 5. If I'm going to find the union of A and C, so I'll have 1, 5, 3, and 4. And then if I'm going to find the union of B and C, I will have 2, 3, 5, and 4. So I don't have to repeat writing 3 again because I already have 3. Next, we have intersection. The intersection of A and B, written as this, is the set of all the elements which are common to both A and B. So if we have the same example, A intersection of B, so the common elements of A and B is 5. So that's it. And if we have A intersection of C, if we try to find the common elements of A and C, there's none. So in that case, I could have an empty set. And then if I'm going to find the intersection of B and C, the common element is 3. So I will only have 3. Next, complement of a set, written as A prime, is the set of all elements which are in the universal set but not in A. So let's have the same example. If we try to find the A complement, so in A we have 1 and 5. So in your universal sets, we will remove 1 and 5. So the remaining elements would be 2, 3, and 4. Next, if we try to find the B complement, the elements in B is 2, 3, 5. So in that case, walay 2, walay 3, and walay 5. So the remaining elements in our universal set would be 1 and 4. And then if we try to find the C complement, okay, so we have 3 and 4, so we will remove 3 and 4. So the remaining elements would be 1, 2, and 5. So these are the complements of A, B, and C. Next, we have the Cartesian products of sets A and B. denoted by A times B, is the set of all ordered pairs, where your A is an element of set A and your B is an element of set B. So let's take, for example, A times B. So my first coordinate would be from set A. So I'll have 1. And my second coordinate should be from set B. So I can have 2. 1, 3. Or 1, 5. Could also have 5, 2. 5, 3. And 5, 5. If we try to find C times A, so my first coordinate should be from C and my second coordinate is from set A. So in that case, I have 3, 1, then 3, 5, then 4, 1, and 4, 5. Now, if I want B times B, first coordinate and the second coordinate would be from set B. So I can have 2, 2. Can have 2, 3. Can have 2, 5. Or I could have 3, 2. Or 3, 3. And 3, 5. Or 5, 2. 5, 3. And 5, 5. Next would be relation and functions. Okay, relation and functions. Relation. A relation is just a relationship between sets of information. The couple pairing and the pairings of students' names and the courses taken are examples of relations. Anything that there is a connection or a relationship. There is a relation. Buti pa si math, may relation. In mathematics, a relation R from set X to set Y is a subset of the Cartesian product of X and Y. If XY, the coordinates XY, is an element of R, then we say that X is related to Y or Y is in relation with X. Example, you have X 1, 4, and then you have the Y negative 2, negative 1, 1, and 2. Then the relation 1, 1, 1, negative 1, 4, 2, 4, negative 2 is a relation from X to Y. Then we have domain. The domain of a relation R is a set of all the first coordinate in the ordered pairs of R. So when we write that one as a set, this is X such that X is an element of set X where X and Y, or the coordinates X and Y, is an element of the relation. And then we have the image. The image of a relation is the set of all second coordinates in the ordered pairs R. So when we write that one as a notation, you have your Y, all values of Y such that Y is an element of the set Y, and of course the coordinates is an element of the relation. So let's take for example the following. Okay, so we have the relation R 1, 1, 1, negative 1, 4, 2, and 4, negative 2. This one. Okay, this one. So in this case, our D of our R, or the domain, would be the set of the first coordinates. We have 1 and 4. Okay, I don't have to write 1, 1, 4, 4. Okay, and the image of our relation would be 1, negative 1, 2, and negative 2. Okay, for the second one, we have 0, 0, 1, 1, 2, 4. So the domain here would be 0, 1, and 2. And then the image would be 0, 1, and 4. And then the third one, we have 0A, 1B, 1C, negative 1D. So our domain here would be 0, 1, negative 1. and then our image would be A, B, C, and D. A function is a relation in which each element in the domain is assigned to a unique element in the image. Meaning, dili magbalik imong first coordinate. So, we denote the function f in this manner, which read as f is a function of x into y. The set x is the domain and the set y is the codomain. If you look at the illustration, this is how the function looks like. So we have here the input. The function then will process it. So in this case, it slices the apple into half. Okay, and this is now the output. So the input here is our domain. The function is the formula. And then the output is our image. Binary operations. So let S be a non-empty set. A binary operation on S is a function from S times S into S such that your X and Y is an element of S. Note that the image of the binary operation is a subset of S. Thus, we say that S is closed under the binary operation. Other way of saying, a binary operation is an operation that applies to two quantities or expressions x and y. So, example, of course, the basic operations are binary operations. Like addition, subtraction, and multiplication are binary operation because when you add two numbers, real number plus real number, the result is real number. If you subtract, the same thing. When you multiply, the same thing. Okay? They are binary operation under the set of real numbers. Subtraction and divisions are not binary operations on the set of natural numbers. Why? Because when you subtract 1 minus 2, the result is not a natural number. The same thing when you have 2 divided by 3, it's a fraction, 2 over 3, and 2 over 3 is not a natural number. So, that's why they are not binary. Okay? Dapat natural number yung result, but since it's not, then it's not a binary operation. Alright, properties of binary operations. Okay, commutative property and associative property. If either one of these is not satisfied, then the operation is not binary. Okay, thank you. If you have any questions, feel free to message me. Bye!